Busse, who's going to talk to us about wall-bounded turbulence and the many phases of surface roughness. So whatever you're ready, Angela.
Yeah. Okay, good. Yeah, thank you very much. So thank you for the introduction. So I will talk today about wall-bounded turbulence and mainly on how surface topography affects near-wall turbulence. Now, the work I'm showing today was done in collaboration with Thomas Jelly from University of Leicester and Sotiris Sarakinos from Glasgow, who conducted the direct numerical simulation I will show today. Now, I will first start with giving a very general introduction to the roughness problem, just to give a background because we have a wide audience with varied backgrounds. Then talk about rough wall parameterization and examples for important secondary parameters that have been identified. And then I will also point out that these two parameters in the roughness height are not sufficient to capture topography effects or all topography effects that matter. By showing an illustration for an example, which shows surface anisotropy also matters, just as an example for further parameters that enter the problem. And in the last part of the talk, I will take a little bit of different viewpoint by looking at the imprint of roughness on near wall turbulence. So if we start very general, then we can describe the roughness problem as follows: that in the default assumption we make in fluid dynamics is that surfaces are smooth and follows the ideal shape we prescribe. Now, in reality, if we look at surfaces, we find that many surfaces show roughness, though that would be deviations from the ideal shape on scales typically much smaller than the size of the object. Now, roughness is of high practical relevance, and this is because there are so many processes that can cause roughness. So, for example, many machining processes leave behind some traces of roughness. There are many fouling processes which cause roughness, so accumulation of deposits on the surface, and also processes like corrosion. And of course, roughness may also be a result of deliberate human intervention. Now, we find that roughness can affect all types of wall-bounded turbulence, ranging from the standard pipe flow to the atmospheric boundary layer, where urban roughness can be considered changing the atmospheric boundary layer on regional scales. Now, we also find that if we look at a real-life example of rough surfaces, that these are in general irregular and typically show features over a wide range of scales. So one may conclude that the surface being rough can be considered almost the default state of a surface, and because once we expose a surface to environmental condition, it will eventually develop roughness. If we consider rough wall turbulence, of course, surface roughness affects the near wall turbulence in many ways. But in today's talks, I will mainly focus on the Hammer roughness function, which is a downward shift in the mean streamwise velocity profile compared to an equivalent smooth wall case. And if we plot this roughness function versus the roughness height scaled by the viscous length scale, then we would expect an increase of delta U plus as K plus increases. By applying a suitable scaling factor, we can match then for our surface the behavior in the fully rough limit to Nicoratz's sand grain roughness data, which is still the yardstick for rough wall turbulence, and then establish equivalent sand grain roughness. We also see here that, of course, the non-universal behavior in the transitionally rough region. Okay, now I want to formulate two key questions in this connection. So first question is, how does the surface topography influence the roughness function and other rough wall turbulence properties? And then the second question, of course, how can we capture and understand this non-universal behavior in transitionally rough regime? Okay, so the first question is one I want to focus about. The second question is much more expensive to tackle using DNS. So now if we consider that we have a wall, and then we may say, okay, it's smooth or rough. Okay, later in this today, we will see also more complex wall options. But if we just look at these two basic options, smooth or rough. Now, if we say the wall is smooth, then our consideration of the wall properties probably just ends here. But if we decide, okay, we consider a rough fall problem, suddenly a lot of extra parameter enter this problem. So we need to consider what is the size of our roughness features compared to typical flow length scales like the viscous length scale or the boundary layer thickness or channel half height. And then we also need to understand, okay, what is the topography of our rough fall? And then we have multiple parameters needed to describe this accurately. So for example, the height distribution needs to characterize spatial distribution, orientation of this rough surface to the mean flow. So basically, once we choose to look at rough fall turbulence, we are not suddenly faced with many new parameters which just rise from the fact that the wall is now rough. Okay, and now we can try to bring some order in this problem by maybe classifying them in primary and secondary roughness parameters. So our primary roughness parameters is the roughness height, which we discussed earlier, and we would expect in general roughness effects to increase with roughness height. And we would see this as our most important roughness parameters. However, we also need to describe the roughness topography, and for this we send the extra roughness parameters, which characterize roughness shape, distribution, orientation, etc. Now, one big problem in this connection in the fluid dynamics community is that we have there no common norms established, unlike other, for example, in tribology, which have international standards to describe roughness characterization. This has led to many different and overlapping parameter definitions to be in use, causing unnecessary confusion. However, in the last 10 or 20 years, I guess most widely investigated secondary parameters are probably the surface skewness and the effective slope, as, for example, also discussed in the review by Daniel Chang. And so before I discuss the secondary parameter, I first wanted to take a step back and bring a problem which illustrates that even a quite simple question already can be unexpectedly challenging once we go to irregular rough surfaces. And to illustrate this, I want to ask a question, okay, what is the height of a rough surface? Now, if you consider a regular roughness, then the definition of the roughness height is straightforward. So for example, if you create irregular rough surfaces by placing roughness elements on a flat surface, you would just take this height of these roughness elements. Now, once you have an irregular roughness, you suddenly have multiple options to define your roughness height. So, for example, a very widely used parameter is arithmetic mean of the height deviations from the roughness midplane. Of course, you could instead use the root mean square of these values, which might be mathematically more appealing since it's connected to the moments of the height distribution. And or you might alternatively use a measure that is related to the maxima and minima of this roughness trace, like the RZ max value, or you could choose a most average value, that the mean peak to valley height, where we divide the signal in 5 chunks and take the RZ max for each of them and then average. And now, depending on which measure you choose, you get quite different conclusions. What is your roughness height? So all these bars are drawn on scale for this signal, and obviously arithmetic mean gives you a much smaller values than if you choose the RZ max. Now, to return to this, I wanted to briefly discuss the two, I guess, secondary parameters which have been most widely studied. These are surface skewness and effective slope. So, just to illustrate them. So, the surface skewness is just the skewness of the height distribution of the surface. And if this is positive, we would in general see this as a peak-dominated surface. If it's negative, a pit-dominated. And if it's approximately 0, as a neutrally skewed surface. So, skewness effects on wall turbulence have been investigated in a number of studies, some of which are mentioned here. So, however, I wanted to just give a very simple example which illustrates the effect of skewness, and this is a pit-peak decomposition we did a few years ago. So we took a full Gaussian rough surface, Gaussian meaning that it has an approximately Gaussian height distribution with 0 skewness, and decompose it into its peaks and its pits. Now, this results in 2 surfaces which very closely matched height measures. So these are given in the first 3 rows in the table, and also similar correlation lengths and kurtosis, but very different values in skewness. So one is highly positively skewed, and the other one is highly negatively skewed. Now, So we can purely now focus on the skewness effects using the surface. Now here we see results from direct numerical simulation of turbulent channel flow at RA tau 395, and you immediately see that the pit surface, so these are the blue line, is a blue line here, gives a much weaker roughness effect than the peak surface. So you also see this in the delta U plus measure. And this is relatively easy to understand if you consider that for the peak surface, the roughness features are exposed to the flow and strongly interact with the flow, causing a high roughness effect. In contrast, for the pit surface, the flow can largely skim past these pits and mainly interacts a little bit with the upstream lips of some of these pits. So this results in overall a much weaker roughness effect. So we also find in the literature and other skewness studies that in general, the roughness effect is expected to increase with increasing skewness. Now, the other parameter that has been widely studied is the effective slope, which is also directly related to the frontal solidity. So here's the definition of the effective slope. So we just take the streamwise derivative of our height map, h of x and y, and then average over the absolute values of this over the surface. And here you see just an example of surfaces which have different effective slope. So this has a high effective slope, this is a low effective slope, but otherwise have very similar surface parameter. Now, as has been, for example, pointed out by MacDonald as well, is that this measure is directly related to the frontal solidity just by a factor of 1/2. And so frontal solidity was already considered by Schlichting in his 1936 roughness study. So this is defined as projected frontal area per total plan area. Okay, just to summarize effective slope effect. So if we consider the roughness function, here's some data from the literature, from simulations and experiments. And so what we see here that for moderate effective slope, we see an increase in delta U plus, and we expect a saturation here at high delta U plus values. Now, I see also a few problems with effective slope, and briefly to discuss them. First problem is what I see as a little bit of lack of independence and parameter overlap. So what I mean by this is that if we, for example, consider skewness, this is independent of the height because it just characterizes the shape of the height distribution. Now, in contrast, ESX is not independent of the height because if we just stretch the height axis of our surface, then we would also increase the effective slope of the surface, and this can sometimes lead to confounding effects that increases in effective slope are observed and roughness effective are associated with this when we maybe should more associate it with the increase in the roughness height. And then the other thing is there are also some contradictory trends. So roughness effect, as we discussed, is expected to saturate with high effective streamwise effective slope. Now, however, we see also studies where the frontal solidity was varied. So these are just some examples from numerical studies using DNS by Leonardi and Castro, MacDonald et al., and also one of our studies. These are all different kinds of surfaces. And you see in this case, if delta U plus is plotted against frontal solidity, then we see here at high frontal solidities a decrease. Now, similar observations have also been made in experiments, of course. Okay, so if we now take stock and ask the question, are now these parameters, so roughness, height, skewness, and effective slope, would they be sufficient to capture rough wall topography effects? And the answer is, from me, is no, because many topography effects cannot be captured by just these three parameters. And to point some out is a very obvious one is surface anisotropy, which I will discuss in detail later. The other one is surface orientation, and also the aspects of clustering and inhomogeneity cannot really be captured by these parameters. And there may be, of course, further aspects that are not captured by just these parameters. So to give an illustration, I wanted to briefly discuss anisotropy surfaces, so irregular anisotropic surfaces. So examples for these surfaces are, for example, machine surfaces, or we also find various degrees of anisotropy on fouled turbine blades, and also geophysical examples for anisotropic roughness like sand dunes or ripples. Now, if we consider our roughness height and the skewness, we have no information about anisotropy contained in them at all. ESX might give us some indication, but by its own, again, it cannot capture anisotropy. So we need at least 2 parameters, and we could use this for this streamwise and spanwise correlation lengths. This would be more consistent with the tribology convention. However, these are quantities that are not so widely studied in fluid dynamics. So we also now considered streamwise and spanwise effective slope. Now, spanwise effective slope was already recognized as a parameter in earlier studies, for example, by Tucker et al. Or Agai Juibari. But we have now here designed a set of surfaces which allows us to really focus specifically on this parameter and discuss its properties. So all these surfaces have a very similar height distribution, which are neutrally skewed. So skewness close to 0 to exclude skewness effects. We have also scaled them to a comparable roughness height. So all the mean peak to valley heights of these surfaces are matched to make them as comparable as possible so that we can just focus on effective slope effects. So the first row are all surfaces at effective slope 0.3, and then as we go down, the streamwise effective slope is reduced. Now in the direction of the arrow, so from right to left, we have increasing a spanwise effective slope. So this surface down here has the highest spanwise effective flow of 0.70, and these have a spanwise effective slope of 0.1. Okay, so now here again, just focusing on the roughness function results again from DNS of turbulent channel flow. And if you first look at the middle panel, then this plots delta U plus versus ESX. And reassuringly, what we see is that we see observed expected increase with a streamwise effective slope. However, we also see now if we plot delta U plus versus ESY that the roughness effect decreases with increasing spanwise effective slope. And this is especially noticeable for the surface which have a low ESX. So the ESX equals to 0.1 surfaces, which are shown here with the red symbol. So these appear to be much more susceptible to ESY effects. We can also attempt an exponential fit if we plot delta U plus versus the ratio of ESY over ESX. And this also fits to our earlier data where we varied streamwise and spanwise correlation lengths of the surface. Now, as we don't claim that this fit is universal, it just fits well to our data here under these specific circumstances where we excluded the effects of surface skewness and roughness height, because they are all matched for all these surfaces. Now, why do these surfaces with high spanwise effective slope have a lower roughness effect? Now, to this, we can consider, for example, the pressure drag contribution to the total drag. So again, this is here shown against ESY for our 3 different sets of ESX surfaces. And now, as we observed, the strongest effect again is for the surfaces with the lowest ESX, and we see here a decrease as we increase in the pressure drag contribution as we increase our spanwise effective slope. And if we look at the surfaces, so these are showing the surfaces for that of streamwise effective slope. So all these have the same streamwise effective slope, but increasing spanwise effective slope. And we can see now that for the highest spanwise effective slope, we have this streamwise aligned structures in the surface which the flow can follow. So we don't get any reverse flow separation as we observe in part of these surfaces. And overall, this reduces the pressure drag effect. Now, to summarize, as I've shown that anisotropy strongly affects the roughness effect of irregular rough surfaces. And I should also, however, point out that there are likely to be surface correlation effects which cannot be captured by just looking at streamwise and spanwise effective slope alone. So one obvious one is, for example, the orientation angle of our dominant direction of anisotropy with the flow direction. So currently we basically just look at examples where this is 0 degree or 90 degree and not at angles in between. And then we also see sometimes surfaces which much more complex direct anisotropy features, like for example, the scan of a scratched ship propeller, where we have multiple direction of anisotropy, and they may potentially exhibit a much more complex behavior. Now, in the last part of my talk, I wanted to briefly discuss a little bit different view on near wall flow behavior over rough walls by looking at the imprint of roughness on near wall turbulence. So this is fairly recent work. So based on a set of surfaces which were inspired by barnacle colonies. So this is a roughness type that tries to represent the fouling of a ship hull surface as it's colonized by barnacles. Now these are idealized surfaces, just showing this effect. So we start off from 10% and go up to 85%. So as more barnacles settle on the surface, their planform solidity would of course increase, but also the frontal solidity, and at the same time the skewness decreases. Now here we see just the basic results for this barnacle coverage study. Now if we just consider skewness alone, we may expect that as we decrease skewness, which would go from this surface to this surface, we would see an increase in the roughness effect. Now in reality, this is not the case, because for this set of surfaces, the frontal solidity effect dominates. So as we go here and decrease our frontal solidity, we first see an increase, see a peak here at the 60% coverage case, and then see a decrease. Okay, now the point I wanted to point out is, or the different concept to look at is by looking at the concepts of the blanketing layer. So this blanketing layer is defined as the isosurface where the mean flow reaches the value of 5 in plus units. So the time average flow field u of x and y z is equal to 5 in plus units. Now 5 is admittedly an arbitrary threshold, but inspired by the smooth fall behavior, where this u plus equal to 5 would correspond to the upper end of the viscous sublayer. So for a smooth wall, this blanketing layer would be just a flat surface offset by 5 delta from the wall location. Now here we see the equivalent blanketing layer for our surfaces, and you see that it looks quite different for the different surface because it bears the imprint of the underlying roughness. However, you see here we can distinguish individual barnacle colonies on the surface, including some smooth section in between, whereas here we cannot really identify individual barnacles anymore. So the question is now, how are these two surfaces correlated with each other? How is the blanketing layer correlated to the height map? Now to do this, we can define a cross correlation factor, and this is plotted here against coverage. And so this would describe how well the rough wall mean flow can conform to the underlying topography. And we see that, okay, it's better to be able to do this for the present case for the lowest coverage, and that this ability to decrease to do this decreases with increasing coverage. That also means that from the perspective of the outer flow, at the highest coverage, the rough surfaces appears probably different if we look at the flow above our blanketing layer. And to quantify this, we can now define parameter space that characterize the topography of our blanketing layer in analogy to the parameters we defined for characterizing the topography of the height map. So for example, if we do this now for the frontal solidity, so this is here delta u plus plotted versus the frontal solidity of the height map, which we have discussed before. So for the present surface, these are the blue dots. And now if we do instead define our frontal solidity based on the topography of this blanketing layer, then we recover a linear relationship between delta u plus and lambda f based on the blanketing layer. Now, this is results we have so far only investigated for this set of surfaces. So I don't claim it to be universal, but it may help us in understanding how the very near wall flow interacts with the roughness topography itself. So to conclude, first, hopefully you appreciate that the topographical characterization of irregular rough surfaces can be seen as a challenging problem in itself, and we should appreciate there's extensive work that has been done on this in the context in the field of tribology. Now, also shown the importance of skewness and effective slope, which have been widely studied in the literature, but that also they can't capture all relevant topographical effects. And as an example, I discussed in depth anisotropy of irregular rough surfaces. Now, other aspects that are not possible to quantify just by skewness and effective slope would be effect of clustering and inhomogeneity, which by itself would pose many other problems. That is, how do we topographical characterize the surfaces? We may end up with rough smooth and smooth rough condition, and then also the emergence of potentially stronger secondary flows. And finally, I just wanted to briefly show the viewpoint of the blanketing layer, which may help us to understand some of how the rough surface imprints itself on the near wall turbulence. Thank you for your attention.
Okay.
We have a few questions. Thank you, Angela.
Thank you.
We'll go over here, I guess.
Thank you for the very nice expose of all the parameters. I had a couple of quick questions. So your DNS is at a RE tau of about 390, I think. Do you have any sense of at what RE tau, for example, these results will become Reynolds number independent?
Well, we already did an earlier study in the context of surface scans, where we looked at how much this would influence by Reynolds number effect, and we found that for basic quantities like delta U plus, we can even use simulation at RE tau 180 to get these. Of course, this mainly for the mean flow properties. So that was published in a paper on analogy for Nicoraz's sand grain roughness, where this was studied in detail.
So for urban roughness, also people look at lambda p, the planar density.
Yeah.
I wonder, you cannot define it for arbitrary roughness like yours. What other parameter does it relate to?
Yeah, lambda p is a little bit of a challenging parameter because it implies that you have smooth section left of your surface, so you can define a planform density. So for these barnacle surfaces, you can do this. Also, our percentage coverage is just the planform density. Now, I would see it more, don't really know how you could justify it for these type of surfaces, which are completely covered by roughness effect. So I don't know whether you could define an analogy, but I think it would be a forced analogy because there are no smooth sections left on these surfaces.
Yeah, Angela, very much. Thank you very much. I have just a quick question to the one of the earlier slides. You showed this delta U.
Yeah.
So that essentially means, and I think that was kind of known, right? That the velocity profile shifts.
Yeah. No, so that was not meant as a new result. It was just introduced.
Right. No, that's fine.
Yeah.
I was just wondering. I mean, this is, well, from a modeling perspective, this is apparently nice, right? I mean, because the shape seems to be preserved, right? So that. At least that's how I see it, is kind of that the internal mechanism, the dynamics of the shear layer in that region is not so much affected. Do you have support for that in your DNS?
Yeah, I mean, it depends really on the roughness shape. So for most roughness, indeed, we find that this shape is preserved. But however, there have been studies, and we also observe it for example, the ESX 0.1, 0.1, ESY 0.1 surface, that we get a loss of outer layer similarity. So, and I think that is potentially a danger for this low effective slope effect. And I believe there have also been studies of this in Melbourne for low effective slope effect experimentally. So, but I think in the majority of rough surfaces, it's probably preserved based on my experience.
Nice talk, thank you. The question, riblets also are kind of roughness. And the question is then, should not be some kind of a measure of simply the degree of randomness of this? Because, well, all these measures will not capture the riblet effect as such. And with the practical thing in falling of riblet surface is an issue. Would be very interesting to see what you can say about this.
Yeah, that's, I agree that's an interesting question. How much dirt can you throw at a riplet surface till it breaks down? It doesn't have a drag reducing effect. So I think I haven't tested it yet. So, but I agree it would be a very interesting question.
Okay, we have a number of people who want to continue to ask questions, but we're in the interest of time. I think we have to move on to the next talk. So we'll pick those questions up in the coffee break or during question and answer or discussion. Discussion tomorrow. Okay. We couldn't slide a little bit with the schedule this morning. We had a lot of people with questions. Yeah. Okay. We'll do a couple questions because this was a good discussion.
Okay.
Can you?
So I thought next one needs to get ready with their presentation, but yeah. So.
Okay, so this one may be difficult to ask without a graph, but when you were plotting your mean velocity profiles early on for a few roughness cases, I think it was for peaks versus troughs.
Yeah.
They looked roughly parallel away from the wall, but not exactly parallel. So I was wondering if you've checked whether there's sensitivity on at what height you measure delta U plus.
Yeah, we did check, and for these, since the outer shape is essentially preserved, it's not sensitive to the exact location. So we have also a paper on filtered surfaces where this is shown in detail with Niels Zandam, and I believe there it was shown in detail. But okay, once you lose, of course, outer layer similarity, then it would become more sensitive to where you actually measure.
So where do you measure?
So these are all so the surfaces with the streamwise and spanwise effective slopes, these were based on measure in the applied in the log layer. And Tom did check for the sensitivity for this, but so the only case were really more sensitive for the one where we lost the outer layer similarity. And the other cases are just based on the central line velocity, which we found at a reliable measure in most cases.
Okay, one last quick question from Beverly.
To say it was going to be quick. Angela, I really enjoyed your talk, and I think the blanketing layer idea is a really nice one. So my question, I'll talk to you about the plot you showed because it seemed to disappear. I think you just showed the portion that was at a fixed height, did you? Because it didn't appear over the clustered barnacles.
And so the blanketing layer is just this implicit surface where you time average field reaches.
I know,
5.
but it should distort over the clusters, right?
Yeah. So it did distort over the cluster and was colored with the height elevation above.
Okay.
So that was the coloring of the surface.
Thank you. So my question was really, I think that the perturbation of that is very much related to the Major Alvarez and Christensen result, right? That you can down select the scales. You can remove scales that don't have an imprint. And so I was wondering whether you'd been able to track back from the blanketing layer to the actual correlate to, well, I mean, it's in that correlation, I think, but can you remove scales and still get the same blanketing layer?
No, I haven't tested this systematically. So these surfaces all had similar scales. We previously looked at this blanketing layer in the context of Reynolds number dependency over flow over surface scans, where I first came up with the idea of the blanketing layer.
Yeah, it's very nice. Thank you.
Thank you.
Okay, let's thank Angela one more time.
Thank you.
And as Daniel gets wired up here, I'll go ahead and introduce him. So this next talk is from Daniel Chung, University of Melbourne, and he's going to be talking about riblets, drag reduction, and heat transfer. And he's going to be using minimal channels to study that.
Okay, thanks. Thanks to the organizers for inviting me to present at this workshop. This is joint work with Nick